cross-document coreference. If I click on this link, you can see that second document, she, is not anaphoric to the first one because it doesn't precede it in the same text. So this is an example where we have coreference which is not anaphoric. Anaphor resolution is one of the most challenging. Anaphor resolution is one of the most challenging tasks of natural language processing, and it must be correctly done, because if it's not done correctly, it can cause some confusion. The results are not very nice. This is a real example from the Second World War. It was a brief award leaflet in the UK. So somebody who reads this text at the beginning will wonder whether you have to put. We have been living in the world of dreams in the 70s, because basically we had systems which were developed only at conceptual level. People wouldn't implement a lot of things in the 70s because they didn't have the tools. And much of the work on anaphor resolution in the 70s was actually never implemented. And
only just begun to live.
I selected this song, We Have Just Begun, because it's a nice song by the Carpenters. And this is because I'm referring to the beginning of knowledge power approaches, which I introduced in '96 at the conference in Lancaster, where I proposed the idea of resolving anaphor in a knowledge porous way, because everybody before me had either done it manually at the conceptual level, or they have actually used full parsing. So this was the first approach, which was knowledge poor. This approach is better known from a paper which I presented at Corning in Montreal '98. Several people also did knowledge poor anaphor resolution. We'll have a look later. But this was the beginning of a new era. Why? Because at that time there was a surge in the development of operational anaphor resolution algorithms, mainly due to the availability of large corpora, parse-speech taggers, and parsers. Before that, we didn't have so many. So this was the beginning of a new era in anaphor resolution, knowledge poor anaphor resolution, where not much knowledge is needed, or where not conceptual, manual sort of crafting is needed. Developments and evaluation of a knowledge poor approaches. I mean, other works were imported, like Kennedy and Bogoraev and Baldwin, more or less in the same time period. After that, in the 90s, late 90s and early 2000s, we had a new trend. This was machine learning. Machine learning used in anaphor resolution, but many papers published suggested that machine learning algorithms were not necessarily better. And now we have something different. Now it's a deep learning world. And I'm starting here with a song by James Brown, '66. It's a man's world. Today, it's not so much a man's world. In many countries, it's mostly a woman's world. But I'm talking about something else, not about whether it's men or women. It's about a deep learning world. In our field, back in 2015, we started basically using deep learning on a larger scale. I mean, all my PhD students since 2016 have been using only deep learning to crack any problem. And today we have something else, the large language model. So it's a large language models world too. So this is a slide which I had from 2018. And this is when basically a lot of people were using already deep learning for anaphor resolution. So we have a lot of papers ever since. Newton is a paper on deep learning for anaphor resolution in Polish. Leo and L is a paper which came out last year, which provides a survey of all the deep learning approach for anaphor resolution. This year, and at the end of last year, we have two papers which actually report the use of ChatGPT for anaphor resolution. In the first case, ChatGPT wasn't that good, unless fine-tuned to a specific domain through prompt engineering. In the second case, the results were not that great either. So those two papers did not show much promise in terms of large language models for enough resolution. So I don't think I have to explain what a large language model is. Most of you know it, artificial networks which contain billions or trillions of weights. And obviously we use a lot the term generative AI with the emergence of not only ChatGPT, but other large language models like Llama and Bard. But I think this is something that everybody knows. I have those slides just for beginners. So large language models have achieved remarkable, in fact, scary results in many areas. And exceptions, at least until recently, the outputs of deep learning models have not been always ideal. I mean, the failure of machine translation about a few years ago to successfully translate multi-word expression was an example that deep learning still had a way to go. Also, I mentioned the work on machine learning approaches to enough resolution, which were not always better than the old-fashioned rule-based approaches. And these are examples, a few tests that I did with machine translation. We were trying to translate the multi-word expression, kick the bucket, which means to die. It's a multi-word expression. This would be a challenge to many machine translation systems. So in 2018, unfortunately, the examples are in Spanish, but I hope you can trust my judgment. Here we have prompt, which delivers a terrible translation in Spanish. Kick the bucket is not translated correctly at all. It is translated literally. Systran does a very bad job as well. And then Google Translate basically does slightly better, but grammatically not correct because it doesn't conjugate the verb. Again, I'm sorry for those examples in Spanish. I don't have ones in Hindi or in other Indian language. DeepL, equally bad. Okay, so which shows that in 2018, deep learning, neural machine translation was not good. I repeated those experiments in 2023. So I tried DeepL, much better, almost perfect. I tried Google Translate in Spanish. The Spanish translation is almost perfect. I tried ChatGPT, equally good. So we have seen a dramatic improvement just in the span of 3 or 4 years. And the objective of this study that I'm going to report is this study had to do with trying to seek whether up-to-date deep learning and LLM approaches, as well as approaches benefiting from modern resources such as eye tracking data, deliver better results than the approaches of the rule-based tradition from the 90s. At that time, we didn't have even gaze data. Gaze data are the data produced by eye tracking. So those are very useful in linguistic studies, and especially in discourse studies. So we used also additionally gaze data in addition to the modern approaches. The test bed was my approach for knowledge poor resolution of enough resolution. So I worked with a colleague, and we built different modifications of the original algorithm. We used different deep learning models and also LLM models, and we also benefited from gaze data. We compared the performance of the enhanced systems and sought to establish whether and to what extent they outperform the original algorithm and which configuration fares best. So now a little bit about the model that we're using, the algorithm that we're using, the testbed. This was my original knowledge poor approach. It operated on parse-speech tagging and noun phrase inflection. It didn't use any full parsing. This is very important. This is why it's called knowledge poor. In addition, it did something very simple as an idea. It located antecedents within the sentence or two at most of the anaphor, because 98% of the antecedents were found to be within 2 sentences. And we did gender and number agreement. And this application, then we applied the so-called antecedent indicators to decide which is the most probable candidate. The noun phrase with the highest score was declared as the winner, as the possible antecedent. So this system was improved in 2003, and in 2006, for instance, we use different. In 2002, we used syntactic parallelism. So those systems were a slight improvement, and there were 100% automatic systems. So I think it's very important to say that in the field of enough resolution, until the late 90s, many of the systems were not automatic. They were semi-automatic in the sense that they would resolve an offer automatically, but then somebody, the user, would post-edit the output, or they would simply remove the, for instance, the non-referential, the so-called pleonastic pronouns, which means that even though they claimed to be automatic, they were not really automatic. So this was an example of a fully automatic anaphor resolution system, and I'm going to use this term because I'm going to show something very interesting on this. So those are examples of antecedent indicators that apply a positive score to an NP which is considered to be a probable antecedent. And then the impeding ones are exactly the opposite. If there's an NP which is not likely to be an antecedent, it receives a negative score. This is an example of a boosting indicator. The first noun phrases get a boost of 1. You can see that it reminds you a little bit of the so-called subject preference and centering for those of you who work in this course, but we didn't have subjects because we did not use a parser. So this is why we had to have this an indicator. And then collocation match is the example here where it is most likely to be key because of the same collocation and not the volume. And this is an example of an impeding indicator where we have the VRC penalized because it's part of a prepositional phrase. So for those of you who would like to learn more about those indicators, there are many papers describing it. In Mars, we had new indicators. I mentioned this, and now I wanted to pay attention to those figures. So we published a paper with a former PhD student of mine, Catalina Halet, where we had an extensive data where we evaluated the fully automatic resolution. So Mars, this is my system, the knowledge work approach did 57%. So you may think that this result is not high, but anaphor resolution is a tough task. So Canadian Bogoraev, which was also knowledge poor, didn't do so well, and Baldwin's Cognac did even worse. And those next two approaches were based on full parsing, Hobbs and Lapin and Lees. They did a bit better, but not much better. But they had the benefit from full parsing. So this was a different game to play, of course. And look at those figures, because the baselines were really poor. Because I'll show you now in a minute what were the figures published in the original papers, which I call it mystery of the original results. During the opening session, evaluation was correctly listed as an important topic. So evaluation is something very interesting and something that sometimes confuses us. So if you look at the original papers reporting those approaches, so Hobbs in the original paper, they report 31%, 32% higher, Lapin and Lees 25. Every paper actually reports a much higher number. Why? This is something confusing. How can we trust the numbers? When we read papers, do we trust numbers? Why all of a sudden the numbers are very high? Do we believe them? Are the authors honest? This is something very important to. And I'm going to give an explanation why those differences exist. So in the field of anaphor resolution, when people reported results, they had different data sets, but they did not care about the complexity of the data sets, because we could have anaphors which could be very difficult to resolve. So basically what we did was we developed an evaluation workbench where actually we computed automatically the complexity of the data by computing the referential distance between the noun phrases and the anaphors, the number of noun phrases or sentences between the anaphor and the antecedent. So this evaluation workbench allowed the comparison of many approaches, and it was something very important for the field of anaphor resolution. The issue of complexity is that not every anaphor is equally easy or difficult to resolve, and this was the issue that the results may differ. But in addition to that, there was something else which I'm going to comment on. First of all, in the papers, no sufficient evaluation details were given. It was not clear what is the degree of automation. This is why I said it is very important that if you have a system, it's either fully automatic or you have to declare it honestly it's not fully automatic. And many of the papers did not exhibit enough transparency and honesty. This is why the result was so confusing. So the evaluation was not very objective. And if you look at this, what is this actually? You think it's a cartoon of a human being? Yes, it is, but it also says something else. If you read it, it says liar. So it says liar because I personally have read many papers where I'm not going to mention authors, where the authors have made up the results. So this is not something that we should do. We should educate our students and colleagues to be honest. And I'm going to say something about honesty. So some people are reluctant to publish negative results. I think this is wrong. We should publish negative results. We shouldn't expect always our approach to be the top one, the best one, because by publishing negative results, you learn what is good, what is not good. And good tradition now, recent tradition at the ACL conferences that they organize workshop on negative results. And I have been pushing this for many, many years. And publishing results is very worthwhile. In 2001, I was invited to be a member of the editorial board of a Canadian journal called Negative Results in Natural Language Processing and Machine Learning. 2000 or 2001, I don't remember. And this journal was published in Canada. So 23 years on, how many papers do you think the journal published? Only one. For 23 years. Why? Because people are afraid to publish negative results, which is wrong. And I'm very glad that now, through the ACL initiatives of negative result workshops, people are now seeing that this is worthwhile. In fact, one of the conferences that I'm organizing now, we explicitly say that negative results papers are welcome. So we should not ignore the negative results, and we should report really the real results. Okay, I'm going to skip this slide, which is not so interesting. So the next one, the next section is about the data methodology of the study that I'm reporting on. So in this study, we looked at two existing corpora in English. Those corpora were annotated. They had actual information about the eye movements of readers, which means gaze data. And those were corpora used by the psycholinguistic community for their psycholinguistic studies. But we actually added another layer of annotation where we added information about the pronoun and the antecedents or locations of the pronouns and the candidates of noun phrases preceding within two sentences. So this is the characteristic of the annotated corpus that you use for this study. The size is okay-ish. Basically, it's not a huge corpus, but in the field of coreference and anaphora, it's very difficult to have a huge one annotated because it's a very time-consuming and language-intensive task. The methodology is that we wanted to see, once again, I repeat, whether the machine learning, deep learning, and LLM techniques, as well as the exploitation of eye tracking gaze data, could deliver better results than the old-fashioned and popular in the 90s rule-based method. And I mean, not only because in the 90s we didn't have deep learning and LLM, but we even didn't have gaze data. So this study tries to do something which the studies that we did in the 90s did not have it. So we produced several modifications of the original algorithm. We incorporated machine learning and deep learning techniques and resources. We actually enhanced the algorithms by optimizing those antecedent indicators that I just showed you. And in addition, features from the original antecedent indicators, basically what we did was each noun phrase candidate was associated with a set of language model features and a set of gaze features. So for each candidate, the sentence containing the pronoun was identified, and the pronoun was replaced by candidate NP, which has a probability, certain probability as to whether it is an antecedent or not. I mean, the probability from the language models were used. And also we had information about gaze features. So now I'm going to show you what are the results. So after deriving the values of the full set features, we conducted experiments to optimize the weights of the various combinations we use to evaluation strategy, tenfold cross-validation and cross-corpus validation settings. In the tenfold cross-validation setting, we use 90% of the corpus for training and 10% for evaluation. And in the cross-corpus evaluation, we trained on the whole corpus. It was one of the gaze data corpora, and then we tested on the other corpus. This was the second gaze data corpus. So we expanded, as I said, we experimented with several machine learning models. We tried to predict whether a candidate NP is an antecedent or not. Of course, everything was on the basis of the annotated training data. Simple linear regressions seem to give very good results, but we also, I wanted to show that, say that by using optimization techniques, we try to improve the accuracy of enough resolution by 10%. And in statistical linear regression model, deep learning language model features secreted variables. Annotated data was learned to train and learn the optimal weights for the variables. As I said, the optimization increased the performance in enough resolution. We also explored the impact of the different configuration on the accuracy of enough resolution, and we compared the accuracy of the original algorithm to the various modifications and configurations which were developed for this study. And those are the effects of optimization. We can see that the optimized settings deliver better results. So the performance goes from 47 to 55 in the case of cross validation and 53 in the case of cross-corpus evaluation. So those are the most important figures of this study. And by the way, the results of this study are reported for the first time at this conference. I've never showed those results because we completed those experiments only last month. So you're the first ones who hear about those results. I was planning to give a talk in Lancaster about this, but it will be after this conference. So you see here different deep learning models. So I have ordered them in terms of performance. So the first one, which does best, is the so-called deep LM token labeling. Those token labeling approaches based on deep learning have been really very good in recent months. So the weighted average is 68%, which is not very high, but for enough resolution, believe me, it's very, very high. Followed by the deep LM token labeling. So this is diabetes V3 large, and this is basically, this is more or less the same, but we use different variations. So ChatGPT, when we offer ChatGPT list of candidates, does quite well as well, 62. So these are the regional weights coming next, enhanced by Daegu deep learning language model. ChatGPT, when we don't offer a list of candidates, does less successfully. Those are different, obviously. This is another deep learning model, and you can see that actually the regional weights are better than some of the deep learning models, like the DeepL models ensemble, and basically you can see that if you use only gaze data, we get 36 only, and those figures I'm going to now summarize, because looking at figures is a bit difficult, but I'm going to summarize the main conclusions. So the main are that the weight of the antecedent indicators initially set empirically can be optimized further. I mean, I've already said this. When combined with deep learning models and gaze features, they work even better. So the inclusion of features from deep learning models using language models improves the accuracy of enough resolution. What about large language models? We experimented with ChatGPT. So when asked to identify antecedent on its own, it performs competitively. I mean, compared to selected deep learning models, but less successfully than others. It cannot beat the original algorithm when combined with gaze data or deep learning model features, or the language model ensemble. So, which means that ChatGPT is not always better than the original approach. It is still far behind the best performing DeepL M-token labeling methods when asked to predict its own antecedents, and it performs better when asked to pick the correct. So there is a configuration where we offer ChatGPT the list of the possible antecedents, and of course, in this case, it doesn't do so well. So with regard to the gaze feeders, they improve the accuracy. They provide no additional information to the models than that use deep learning. The interesting observation is that the two sources of information appear to be redundant rather than complementary. So, do I have 5 more minutes? Maybe I need maybe 5, 6, 7 minutes. So basically, the rule-based models, they don't always perform less successfully than the models based on deep learning and gaze data. In some cases, they have even better results. Data-driven approaches generally fare better in these experiments, but still have a long way to go to beat comfortably the old-fashioned and rule-based models. And basically, here, this is what I said already, that the inclusion of gaze features helps, but they don't provide additional benefit to deep learning models. So this is one against the whole table, because this table actually shows the result. So now I'm going to say, just to finish this presentation, the conclusions, 1 minute, and a glimpse into the future, maybe 5 minutes. So the conclusion is that that old-fashioned rule-based models and enough resolution still have a place in today's research, because they're not always easily beaten by deep learning and large language models. The interesting thing is that we have now the large language models. So what is the limit of enough resolution? We have seen performance 40%, 50%, 60%, but nothing more. So now there is a hope that with the large language models, we could actually make enough resolution work better. And this is the question: how far can we go when we use large language models? Because over the last 40 years, I have been working on enough resolution since 93, 94, and the improvement has been incremental, only incremental. So at the ACL conference 2017, I had invited a talk on coreference resolution, and I posed the question: is coreference and anaphora, are they actually beneficial to NLP applications? And then I had a keynote speech at DART 2007, another keynote speech at TCD 2012, where I reported that there is some improvement, but it's not statistically different, not statistically significant. And I asked a then student of mine, Constantino Rosan, now professor in Surrey, to try to see when, what would be the minimum success rate of enough resolution in order to benefit summarization, and we found that it was 80%. So unless we have 80%, we don't improve NLP applications. This is very important. And now, how good will be AI in the future? The last 3 minutes. So I'm going to define 2 types of intelligence: the human intelligence, which is the linguistic intelligence, the art of writing good texts, and the artificial intelligence, which is the machine intelligence. So linguistic intelligence, I define how good are humans in writing good text. So if you go back into the history, my question is, do we have today people like Shakespeare, Goethe, Cervantes, Pushkin, Alighieri? Some of you may say yes, some of you may say no, but let's assume that today we don't have much better people than those, which means that the so-called human linguistic intelligence, which I defined, has not developed that much in the time. So I did those slides a couple of years ago. So this shows the computer intelligence, because the computer developed, the first computer was developed in the 40s, and this is the human intelligence. We agree, if we agree that we don't have better people than the geniuses of the past, that this human linguistic intelligence has not developed much. This is why I have this bull line here, constant. But here the computer intelligence is going up because we have AI now. But so many people ask me at conferences to predict the future of NLP or predict the future of translation technology. How far can it go? I'm not a clairvoyant. I wish I were. If we humans are clairvoyants, we'll be all very rich, but we're not. So at that time, it was about 1.5 years ago, I predicted that basically the computer intelligence, the machine intelligence, the AI will go up, but it will never cross the bull line, which is the line of human intelligence. So now with the large language models, I'm starting to think whether this thing that I did 1.5 years ago will stand, whether I should maybe revise this prediction. I still think that LLMs will not get as good as humans. This is what I think. But this is my opinion today. Maybe next year I'll have to change this. We never know. So we have to actually embrace the new technology, and for us, AI shouldn't be an enemy, it should be an opportunity. But I'm going to finish with this example from an Afro resolution again, just to show you how difficult it is for large language models to match humans. If you read this sentence, which I took from the Guardian newspaper in 2000, this was at the time when I was writing my book on enough resolution. Does anybody know who is he? Or he, or his? Most people get it wrong. They say it's Peter Mandelson or Tony Blair, but it's neither of them, because Peter Mandelson cannot demand his own resignation, and obviously he is not neither Peter Mandelson nor Tony Blair. He is somebody else, an imaginary character, the imaginary Peter Mandelson of being the prime minister. So this is a very difficult example to solve for humans. I experimented with ChatGPT and it failed, of course. So ChatGPT doesn't get it right. Some human get this right, but ChatGPT always gets it wrong. So you see, there's a lot of way to go. So I'll be delighted to collaborate with students and staff from India. Thank you once again for inviting me.
Thank you, Professor Vitkov, for an illuminating presentation, I should say. And this is now time for question answer. Is there a mic in the hall which can go around? No, that's okay. Then you can simply raise your hand and speak loudly. Okay. Questions, comments? Yeah.
Thank you, Professor Vitkov. Very illuminating presentation. I have a question on one of your last slides where human linguistic intelligence remaining constant and the machine's linguistic intelligence is growing up. But I have my doubts about that. My belief is as we are consuming synthetic language generated by the machines, especially with generative AI, our human linguistic language intelligence is going down, or at least the creative boundaries are being now established by the machine rules or by the boundaries of the machine. So what is your comment on that?
I mean, first of all, I think that we don't have to take people like Shakespeare and Goethe and Cervantes, but I did not want to put it on my slides because I'm just making a claim against humanity. So I simply put the line constant so that I don't accuse any contemporary writers. So I believe that what you're saying is that sometimes the machine constrains our creativity. This is true. I mean, machines do constrain our creativity. I mean, now if we go somewhere, we don't rely anymore on our intuition and maps. We just use our phone. So somehow the machines are making us a bit lazy. And I think that I don't know what to say about whether the human intelligence is stuck or it goes down. This is something probably not for me to reply. Maybe this is something that we need to take an informed joint view. But I think that I do believe in human intelligence, and I believe that I'm one of those who believe that the large language models in AI will not outperform us. They'll get very close to us, but will never do. But this is my personal view. Maybe others have different view.
Thank you very much for the wonderful presentation. So the question is, if you look at the GPT-3 transformer model, it makes a prediction of the next word based on 32,764 words as seen already. There are 100 layers of transformer layers, right, to make predictions about it. If you have seen this movie Titanic, there's a water, right? They're not real water. There's all computer generated water, but you can't help feeling there's a water actually. So I would like to understand what is the nature of, is human intelligence not the GPT-3? What is the nature of intelligence?